Hello guys, welcome to reinforcement learning series, and in this video we're going to see DQN implementation. And for that, first you have to create a directory DQN Pong. We're going to see the DQN working on Pong basically. So the first step, we'll create wrappers. So let's begin. First we're going to create a directory, say lib, and inside that we'll create a first file, wrappers .py. Okay, the first step will be we're going to import the libraries. Import cv2, import gem dot spaces, very important. Import numpy, the very important library in machine learning and data science. Oops, I think we didn't step enter. Okay, and collections. Now, so we will be creating our first wrapper class, that is class fire reset environment and gem wrapper init. Okay, so now we'll check for some assertion conditions. Environment unwrapped get action meanings 1, fire, and one more assertion, length environment unwrapped you get action meanings 3, def step action, and return. Definitely we're going to receive output this step. We're going to take in the specific environment. The action we're going to take, so environment step action, and the reset function self dot environment dot reset, and observations, the done flag, and this is going to be the step. If done, self dot environment dot reset, observation, done, self dot environment dot step 2, if done, self dot environment dot reset, and finally we will return the observations. Okay, so basically this wrapper presses the fire button in environment that requires that for the game to start. And in addition to pressing fire, this wrapper checks for several corner cases that are present in some games. And now we will move towards creating another wrapper, that is the class max and skip environment gem wrapper diff init environment none skip 4. So super net and environment, and now it is going to be, you know, self observation buffer, collections, DQ, the max length is going to be 2. So this is it, and basically this is what we are doing over here. This is the most recent raw observation from, you know, max pooling across time steps. And one more thing we'll do is self skip def step and self action. So total reward 0.0, okay, done, flag none, and for in range self dot skip. So first we need to track the observations, basically the output of the action that we have taken this in the environment as a step. Reward, done flag, and information. So self dot environment dot step action, and whatever the observation we will have, we are going to append it in the observation buffer. Okay, perfect. And definitely going to add up the reward, whatever reward we have got. Okay, and we are done. Then we will definitely break out, otherwise we will continue. Max frame, that is np.max, np stack, and self observation buffer, and x is 0, return max frame, total reward, done, info. Def reset self observation buffer clear, and observation self environment reset self observation buffer dot append observation, return observation. So this is it, and basically this wrapper combines the repetition of actions during keyframes and pixel from 2 consecutive frames. So this is its job, and we're going to create one more wrapper, class process frame and gem observation wrapper, def init, okay, environment is going to be none. So what changes we are going to do? Self dot observation space and gem spaces box and low. We're basically going to taking the intensity of pixel, that is lowest is 0 and the highest is 255, that is we all know. shape we're going to take is 84 comma 1, retype npUint8 observation self observation. We're going to return the process of the observation. Now we'll create this process function. So if like frame size is 210 160 into 3, it is going to be frame okay, fine. Image, we're going to reshape it. It is found to be this resolution. Then we're going to reshape it to 263 as into a float 32. So let's do it. Reshape frame 163, and basically as type we need it to be float 32. And elif frame size is found to be 250 160 to 3. We are again going to do the same, so let's just copy paste from here to and just paste it over here. Else assertion we need to take is false, as we're going to throw unknown resolution. Okay, and again we will check img. Zero 0.299 and plus img 1. Basically what we will be doing, we will just convert input observation from the emulator, which normally has a resolution of like 210 into 160 with RGB color channels, to a grayscale 84 into 84 image. So then we will do some basic resizing and cropping of top and bottom part of the result. So let's do it. 0587 img, that is our image basically, to have it 0.114. okay, and we're going to resize it. Resize cv2 dot resize. We have that resize function already. img 84 and 110, and interpolation, it is going to be inter area. Yeah, xt, the resize screen we're going to take 18. So this is the cropping we're going to do. Okay, and we will reshape it, np dot reshape, and we're going to convert it into our grayscale basically 84 and only one channel, and finally return the X as type of int8 integer. Okay, perfect. So just like I said, the goal of this wrapper is to convert input observation from the emulator, which normally has a resolution of 210 into 160 pixel with RGB color channels, to a grayscale 84 into 84 image, and thus using a color metric grayscale conversion, which is closer to a human color perception than a simple averaging of color channel, then resizing of the image and cropping the top and bottom parts of the results. That's it. Now we're going to create one more wrapper, class buffer wrapper gym observation wrapper def. Let's do okay. Some extra things we'll take over here is the n steps as well, and the data type will be definitely float 32, no doubt in that. Okay, so self dot data type is going to be data type, and whole space gym observation space. Okay, and this self dot observation space is not gym, it's going to be environment observation space. Gym directly doesn't have an observation space, and it is going to be the gym, say spaces box, and whole space low repeat n steps x is 0, and whole space high repeat n steps x is 0, and data type is going to be data type as it is, and that's it. And one more function of resetting the environment, so self dot buffer np dot zeros zeros like self observation space dot low d type, and self dot d type again, and finally return self observation self environment reset. Bingo. And one more we're going to have is the def observation and self observation self dot buffer the last one, self dot buffer. Okay, and self dot buffer -1. Oops. This is going to be the observation. Okay, finally we will return the self dot buffer. Yeah, done. So this class creates a stack of subsequent frames along the first dimension and return them as an observation. The purpose is to give the network an idea about the dynamics of the objects, such as speed and direction of the ball in Pong, or how enemies are moving. This is a very important information which it is not possible to obtain from a single image. So that's it. Now I'll create one more wrapper, basically to give the PyTorch the suitable format it wants. So let's say class image to PyTorch gem observation wrapper diff init okay, and old shape self dot observation space shape and new shape old shape -1 old shape 0 old shape 1 and self observation space gem spaces box low 0 high shape new shape, and data type is definitely going to be float 32 observation we're going to have is self comma observation, and no, what happened, just return the np move axis and observation to 0. Okay, fine. So basically, just like I said, so this is a simple wrapper that changes the shape of the observation from height width channel to channel height width format required by PyTorch. The input shape of the tensor has a color channel as the last dimension, but PyTorch convolution layers assume the color channel to be the first dimension. So this was the only thing, and finally we're going to normalize our values. So one more class scaled float frame gem observation wrapper observation no return np array and observation as type it's going to be np float 32 and we're going to divide it by 255. That's it. So here we have to write observation. Okay, fine. So basically this was the final wrapper we have in the library, so that converts the observation data from bytes to floats and scale every pixel's value to the range of 0 to 1. That's going to be 2.50. Okay, so finally we're going to call all of them. So def make environment and environment name. Okay, and environment gym, make environment name, environment max, skip environment, and again environment, fire reset environment, and then going to process frame. So there's the environment and image, that conversion, height width, channel to channel height width. Input provide will be environment, and environment again, buffer wrapper, and finally we need to normalize. Here we go. And for buffer wrapper we also transform. Okay, done. Bravo. So the wrappers are ready. So now we'll move towards creating DQN model. So let's begin. So let's create DQN model. Here we go. DQN model.py. Okay. So basically the model published in Nature has 3 convolution layers followed by 2 fully connected layers. All layers are separated by rectified linear unit, ReLU, nonlinearities. The output of the model is Q values for every action available in the environment without nonlinearity applied, as Q values can have any value. The approach of having all Q values calculated with one pass through the network help us to increase speed significantly in comparison to treating QSA literally and feeding observations and actions to the network to obtain the value of the action. So let's implement it. So first we're going to import the library, import torch, import torch.add, import numpy, DQN and module def init self input shape and actions super DQN self init. Okay, the convolution layer. So sequential. Fine. So first layer is going to be the convolution layer, of course. Input features is going to be the input channels, that is going to be input shape 0, and output channels is going to be 32, and kernel size 8, and stride will be of 4. And now we'll have ReLU. Fine. And one more convolution layer. Okay, so this time input channel is going to be 32, output channel is going to be 64, kernel size we will have is 4, and stride will be of 2, and again ReLU. Okay, and one more convolution layer. Both input channels and output channel 64, kernel size 3, and stride will be of 1. Okay, and ReLU. So this is done, and a convolution out size self get convolution output, then input we'll give is input shape. Okay, fine. And self fc and then sequential, and first thing is going to be linear layer. Input features is going to be convolution out size, and output feature is going to be 512, and definitely one more relu, and post that a final linear layer. Input feature is going to be 512 and the output is going to be an actions. Okay, so this part is done. So to be able to write our network in a generic way, it was implemented in two parts, convolution and sequential. PyTorch doesn't have a flatter layer that could transform a 3D tensor into a 1D vector of numbers with the requirement of feeding convolution output to the fully connected layer. The problem is solved in the forward function, where we can reshape our batch of 3D tensors into a batch of 1D vectors. Another small problem is that we don't know the exact number of values in the output from convolution layer produced with the input of given shape. However, we need to pass this number to the first fully connected layer constructor. One possible solution would be the hard code this number, which is a function of input shape for 84 into 84 input, and the output from the convolution layer will have 3136 values. And however, it's not the best way, as we all know, as our code will become less robust to input shape change, and the better solution would be to have a simple function, that is this get convolution output, that accepts the input shape and applies the convolution layer to a fake tensor of such a shape. The result of the function would be equal to the number of parameters returned by this application, and it would be the fast, as this call would be done once on model creation, but also it would also allow us to have a generic code. So let's have it. Def get convolution out self dot shape and convolution torch zeros and one shape. Finally return the integer and the size. Okay, done. And one more way forward. Convolution out self convolution x and view size and 0, return self fc, this is the convolution out. Okay, so the final piece of the model is the forward function, which accepts the 4D input tensor. The first dimension is a batch size, and the second is the color channel, which is our stack of subsequent frames. The third and fourth are image dimensions. So the application of transformation is done in two steps. First, we apply the convolution layer to the input, and then we obtain 4D tensor on output. This result is flattened to have two dimensions, a batch size and all the parameters returned by the convolution for this batch entry as one long vector of numbers. So this is done by the view function of the tensor, which lets one single dimension be a -1 argument as a wildcard for the rest of the parameters. For example, if we have a tensor t of shape 2, 3, 4, which is a 3D tensor of 24 elements. We can reshape it into 2D tensor with 6 rows and 4 columns using tview64 definitely. This operation doesn't create a new memory object or move the data in memory. It just changes the higher level shape of tensor. So the same result could be obtained by tview -1, 4 or tview 6, -1, which is very convenient when your tensor has a batch size in the first dimension. Finally, we pass this flattened 2D tensor to our fully connected layers to obtain Q values for every batch input. So this was our DQN model, and now write the training code of this DQN model. So let's begin. So we're going to create a file, say dqn pong.py, and now we're going to implement the training code. So the epsilon decay schedule that was used is also not the best for a single Pong game. In the training, DeepMind linearly decayed epsilon from 1 to 0.1 during the first million frames obtained from the environment. However, in the experiment that I've shown for Pong, it's enough to decay epsilon over the first 1,50,000 frames and then keep it stable. So the replay buffer also can be much smaller, like 10,000 transition, and will be enough. So now I'm going to implement the training code, but before that I want to let you know my PC specs. So it is NVIDIA GTX 3060 Ti and using Ryzen 7 with 16 GB RAM. So let's begin, and the first step is going to be import the libraries. So from lib import wrappers, now from lib import dqn model and import argparse, import time, the most important machine learning library, numpy, import collections, import torch, import torch nn as nn, import torch dot optimizers as optim, from insert board x import summary writer, default environment name, it is going to be Pong, no frame skip, mean, reward boundary, and gamma 0.99, batch size 32, replay size learning rate, target frames, replay start size, now the epsilon decay, frame, and 10⁵ epsilon 1.0 epsilon final 0.02. So basically right over here, so these two values set the default environment to train on and the reward boundary for the last 100 episodes. To stop training if you want, and you can redefine the environment name using command line. And so the parameters right over here are gamma values for like the Bellman approximation. The batch size sampled from the replay buffer is the batch size. So, and the maximum capacity of the buffer is the replay size, and the count of frames we wait for before starting training to populate the replay buffer is the replay start size, and the learning rate used in the Adam optimizer, which is used in the example, is the definitely learning rate. And what is sync target frames? So it is the how frequently we sync model weights from training model to target model, which is used to get the value of next state in the Bellman approximation. So that is sync target frames. And right over here, so the last batch of hyperparameter is related to the epsilon decay schedule, and to achieve proper exploration we start with epsilon 1 at the early stages of training, which causes all actions to be selected randomly. Then during the first 1,50,000 frames, epsilon is linearly decayed to say 0.02, which corresponds to the random action take in 1% of or 2% of the steps. And a similar scheme was used in original DeepMind paper, but the duration of decay was almost 10 times longer. So epsilon say 0.01 was reached after a million frames. Okay, so now we're going to write the code for experience replay buffer. So let's begin. So right over here, class experience buffer def init self capacity self dot buffer settings dq max length capacity length self return length self buffer def append self experience self dot buffer append experience and sample self batch size and indices say np random choice, the length of buffer batch size, replace false, states action, rewards done, next states zip, and self buffer id index for that, and index for index and indices, return np array states np actions rewards d type np load 32 and np runs d type uint8 and np array next stage. Fine. So now basically the experience replay buffer, so the purpose of which is to keep the transition obtained from environment. This is the tuple of the observation, action, reward, the done flag and the next state. So each time we do a step in the environment, we push the transition into buffer and keeping only a fixed number of steps. In our case, so 10,000 transitions definitely. For training, we randomly sample the batch of transition from replay buffer, which allows us to break the correlation between subsequent steps in the environment. So most of the experience replay buffer is quite straightforward. It basically exploits the capability of DQ class to maintain the given number of entries in the buffer. So specifically here in our sample method, we create a list of random indices and then repack the sample entries into numpy arrays for more convenient loss calculation. And the next class we need to have is an agent which is going to interact with the environment and save the result of interaction into experience replay buffer that you have just seen. Class agent and def init. Okay, and definitely environment and experience buffer. So we have it and self.env is equal to env, and the experience buffer we are going to have. Okay, bravo. Now self dot reset as well. So def reset self and self dot state environment reset. Okay, self dot total reward. So during the agent's initialization, we need to store references to the environment and experience replay buffer, tracking the current observation and the total reward accumulated so far. Def play step net epsilon 0.4. CUDA done reward none if random okay is less than the epsilon value, then action is going to be a sample, that is the action. Okay, fine. Else the state is going to be np array and self state copy false, and state v torch tensor, and state to device fine, and the q vals a, so q vals is going to be the output of the network, which we provide the input as the states, and the maximum value torch max q vals v dim, and action is going to be in item done. Okay, so this part is completed, and the main method of the agent is to perform a step in the environment and store its result in the buffer. To do this, we need to select the action first with the probability epsilon passed as an argument. We take the random action, otherwise we use the pass model to obtain the q values for all possible actions and choose the best. So new state and reward is done. Self dot environment self dot total reward. We're going to add up the reward in that, and the experience. Okay, self dot state action reward fine, and is done flag, and the new state. Okay, so the self, we're going to append the experience into the experience buffer. So here we appended it, and the state will be updated. State new state. If is done reward total reward self dot return, and okay. So as the action has been chosen, we pass it to the environment to get the next observation and reward, store the data in experience buffer, and then handle the end of episode situation. The result of the function is the total accumulated reward if we have reached the end of the episode with this step, or none if not. Now it is time for the last function in the training module, which calculates the loss for the sample batch, and this function is written in the form to maximally exploit GPU parallelism by processing all batch samples with vector operations, which makes it harder to understand when compared with a naive loop over the batch. So yet this optimization pays off. The parallel version is more than 2 times faster than an explicit loop over the batch. Okay, so here is the loss expression we need to calculate. So loss is equal to Q of SA and minus reward plus gamma max from A to action, and Q as the future state direction. Okay, so for steps that aren't at the end of episode, or LQSA minus R whole square for final steps. Def calculate loss and batch net target network and device, which is definitely going to be CUDA. And what a batch is going to consist of: states, actions, rewards, the done flag, next states. States, torch, tensor, states, device, next, torch, tensor, next states, to device. Torch, tensor, and actions to device, D-type, torch, int64, and rewards. It's going to be torch, tensor, rewards to device. So we are putting everything into the device CUDA, so it could be provide a computational boost during the training process, as we are going to use CUDA, torch, tensor, guns to device, and D-type torch boolean. Okay, so this is a very simple and straightforward code. We wrap individual numpy arrays with batch data and PyTorch tensors and copy them to GPU, as we have specified CUDA for the device. And now state, action, values, net states v, gather, one action, unsqueeze, and squeeze again. So basically we pass observation to the first model and extract the specific Q values for taken actions using the gather tensor operation. And the first argument to the gather call is a dimension index that we want to perform gathering. In our case it is equal to 1, which corresponds to actions. And the second argument is the tensor of indices of element to be chosen, and extra unsqueeze and squeeze calls are required to compute the index argument for gather functions and to get rid of extra dimension that we created the index should have the same number of dimensions as the data we are processing. Keep in mind that the result of gather applied to tensor is a differentiable operation that will keep all gradients with respect to the final loss value. And next state values, that is going to be target network, and the next states with max. Okay, so we apply the target network to our next state observation and calculate the maximum q value and along the same action dimension 1. And so function max returns both maximum values and indices of those values, so it calculates both max and argmax, which is very convenient. So in this case we are interested only in values, so we take the first entry of the result. Next state values, the done mask. Okay, so here we make one simple but very important point. If transition in the batch is from the last step in the episode, then our value of the action doesn't have a discounted reward of the next state. As there is no next state from which to gather the reward, this may look minor, but it is very important in practice. Without this, training will not converge. Next state values, next state values dot detach. Okay, so we detach the value from its computational graph to prevent gradients from flowing into the neural network used to calculate Q approximation for the next stage. So this is important, as without this our backpropagation of the loss will start to affect both predictions for current state and the next state. However, we don't want to touch predictions to the next state, as they are used in the Bellman equation to calculate reference Q values. To block gradients from flowing into this branch of the graph, we are using detach method of the tensor, which returns the tensor without connection to its calculation history. Expected state action values, next state values into gamma plus rewards, and finally return the neural network. Let me see, loss, state action values, expected action values. Okay, so finally we calculate the Bellman approximation value and mean squared error loss. This ends our loss function calculation, and finally the rest of the code is our training loop. So let's begin. If name is equal to parser and argparse argument parser add CUDA default false action store true enable CUDA parser add argument env default environment name, and into name of environment, default environment name. Okay, arguments is going to be parser parse args device torch dot device CUDA. So we create a parser of command line arguments. Our script allows us to enable CUDA and train on environment. They are different from the default. Wrappers make environment arguments environment next DQN model environment observation space dot shape and environment action space n, and we're going to put it to the device. So here we create our environment with all required wrappers applied, the neural network that we are going to train and our target network with the same architecture. In the beginning they will be initialized with different random ways, but it doesn't matter much as we will sync them every 1000 frames, which roughly corresponds to one episode of Pong. And of course we need summary writer, so we're going to summary writer comment trend network and buffer experience buffer replay size agent sorry agent environment buffer and epsilon start. Okay, so we create our experience replay buffer of required size, and episode it is going to be it's not EAPSST, sorry, epsilon, and the speed is going to be speed. Okay, so we should be printing it so that we have a complete supervision over what is going on. And we're going to write the summary as well. Right, add scalar epsilon frame index, write add scalar speed its frame index first of all. Okay, so done. And again one for the reward, writer adds scalar the mean reward. We're going to check index and writer add scalar reward frame index. That's it. Okay, so in this block, basically this one, we ask our agent to make a single step in the environment using our current network and value for epsilon, and this function returns a non-null result only if this step is the final step in the episode. It's a very important part. So in that case, we report our progress. Specifically, we calculate and show both, in console and the tensor board. The speed is basically speed as a count of frames processed per second, count of episodes played, mean reward after after last 100 episodes, and the current value for epsilon. So let's move ahead. If best reward is none or best now we'll check for the condition that if best mean reward is none or best mean reward is less than the mean reward, we're going to save that specific model. So first let's write the full names. Okay, if best mean reward is none or best mean reward is less than the mean reward, then we're going to save that specific model, torch save net predict, okay, and argument environment plus best for that. Okay, so the model is saved. Now if best mean reward is not none, and we're going to print it. So best mean reward updated, it is going to be best mean reward with the mean reward. Okay, fine. Best mean reward and if mean reward is greater than the rewards that we have, they're going to print solved in this much amount of frames. Oops. Okay, and we're going to break out of the loop. Every time our mean reward for the last 100 episodes reaches a maximum, we report this and save the model parameters. If our mean reward exceeds the specified boundary, then we stop training. For Pong, the boundary is 19.5, which means winning more than 19 from 21 possible games. As we have seen over here at the top, like it was 19.5. Okay, and the one more thing, if length of the buffer is less than the replay start size, we are going to continue if frame index sync target frames target net load state index, it is going to be net state deck. Okay, so this part is done. So here we check whether our buffer is large enough for training. In the beginning, we should wait for enough data to start, which in our case is 10,000 transitions. The next condition, sync parameter from our main network to the target network every sync target frame, which is 1000 by default. And finally we are going to optimizer zero grad and batch, it is going to be buffer sample batch size, and loss is going to be calculate loss batch net and target net device and optimizer step, and finally we'll close the writer close. Okay. So the back propagation step also we miss, yeah, backward. Alright, so and why this target net is showing like this? Okay, maybe we not initialize it, so definitely target net is going to be just like the initial network. Okay, fine. So the last piece of training loop is very simple but requires the most time to execute. We zero gradients and sample data batches from experience replay buffer, calculate loss, and perform the optimization step to minimize the loss. So this was the training part. Okay, so let's start the training. So first we are going to activate the environment. The name of my environment is Torch Test. I hope you have set up your Cura environment. So let's start the training by executing the file. Alright. So here we go. And the training is started, and this is going to take a while, maybe hours. Thankfully we are using NVIDIA 3060 Ti,
so it is not going to take much time. Just it is going to happen in 3 hours. So make sure you have a powerful GPU, and meanwhile you can take a break, watch a movie, and get back to work, and just take a break. Okay guys, so training has come to an end. So the training part is completed. So the training process is just one half of the whole. Our final goal is not just to train the model, we also want our model to play the game with a good outcome. During the training, every time we update the maximum, the mean reward for the last 100 game, we save the model and Pong no frame as s.dat file, and we can load the model file and play one episode displaying the model dynamic. So the code is going to be very simple, and it can be like magic, seeing how several matrices with a million parameters can play Pong with superhuman accuracy by observing only pixels. So let's create the file, then dqn play.py. Okay, so we are going to import the library, import gem, and definitely import time, import art parse, and okay, the most important machine learning library that is greatly utilized in machine learning and data science work, NumPy and Torch. Okay, from lib we are going to import wrappers, and dqn model selections, default environment name, Pong no frame, skip environment version. Okay, FPS it is going to be 25. So we import the familiar PyTorch and gem modules. The preceding this frames per second FPS parameter specify the approximate speed of the shown frames, and now if name is equal to main and parser parse argument parser add argument model required true, model file to load, parser add argument and -e environment and default, so default environment name and help environment and name to use default again default environment name. All right, parser add argument record help. So basically this is going to be the directory for video. Alright, and a parser add argument
no equals, so default true, bst with help disable visualization, action false, parser okay. So basically this script accepts the file name of the same model and allows the specification of the gym environment. Of course the model and the environment have to match. Additionally we can pass -r, that is the name of the directory, which will save a video of the game using a monitor wrapper. And by default the script just shows frame, but if you want to upload your model's gameplay, you can upload it anywhere on your YouTube or your Instagram, anywhere. So that is going to be saved in the directory now. So environment wrappers make env arguments, all right, and if args dot record, then environment is equal to gym wrappers monitor and environment args record, fine. Next, dqn model dqn and monitor. So basically it is going to have environment observation space shape, environment action space dot n, arguments dot model, so map location lambda stg, and I'm going to load the model. Okay, fine. So the state first is going to reset the environment. So here we go, and the total reward we will initialize as 0.0. So collections counter. So this code is very clear. We create the environment and our model, and then we load weights from the file passed in the arguments. The argument map location passed to the torch load function is needed to map the loaded tensor location from GPU to CPU, and by default torch tries to load tensors on the same device where they were saved. But if you copy the model from the machine you use for training with a GPU to a laptop without a GPU, the location need to be remapped. So let's go further, and while true start time dot time args.biz environment render state v and torch tensor np array state and copy false q vals state v and data dot numpy 0. Okay, action np argmax qvals and c. So this is almost an exact copy of agent class method by placestep from the training code. Without the epsilon greedy action selection, we just pass our observation to the agent and select the action with maximum value. The only new thing is the render method in the environment, which is a standard way in the gym to display the current observation. So let's go further. After we're going to have the state reward and the flag after taking a step in the environment action. Okay, so the total reward will be the reward will add up to the total reward. Fine. And if that's end of the environment, we're going to break out from the loop, and if args dot visual delta fps minus time, and we're going to subtract the start time. Okay, if delta is greater than 0, then we're going to sleep. Alright, and finally we are going to print the total reward alright, and the action count counts if args dot record environment dot close okay, fine. So the score is simple. We pass the action to the environment and count the total reward and stop our loop when the episode ends. After the episode, we show the total reward and the count of times that the agent executed the action. So that's a very simple part. Okay, so let's run it now. So Python dequin play, the model name, fine. So you can see it has started playing. So the green one is performing really well. So let's see it. Well, it's playing pretty nice. Okay. So this is basically the visualization of the how our model is working. You know, this is basically. So it's going really nice. You know, really superhuman performance. Maybe it can beat even a superhuman. So, and it's really fast and quick at the same time. So we can see that it's 0, 12, 13. Oh my god. And 14. So it's going in the right direction.
like it is able to, you know, track the ball and, you know, playing nicely to get the maximum rewards. Okay, and boom, 19. Okay, 20, and yo, we won the game. So total reward 21. So that was DQN play, and I hope you have now clear with this DQN Pong. So this was the implementation, and you could try it on some other environment as well. So thank you for watching the video, and please share the video and subscribe the channel.